converges absolutely, then it converges. So if it converges, it may not converge absolutely, but if the sum of ANs converge absolutely, then it converges. That's an important fact. And the proof is very easy, the idea. Of course it converges, because if I'm estimating the sum, the Cauchy criterion says look at the tail. K goes from n to m. But that's bounded by the sum of a sub k's. And this tail goes from n to m. But this is the tail of the absolutely convergent series. And you know this is small by the Cauchy criterion. So this is small by the Cauchy criterion for the series sum of a sub k. So if you can make that small, use the same big N for a given epsilon to make this small, and you're in good shape. Okay, so one of the things that's, so I've given you one reason why absolute convergence might be interesting. That is, it makes certain things that aren't nice, nice. Okay. Here's another situation where things might go really bad if a series doesn't converge absolutely. And that's the last topic today, is the topic of rearrangements. So if you take a series, you might ask, well, what if I sum things in a different order? So here's a question. Let's suppose you have a sum of a series and it converges to some big sum A, some sum A, big A. Here's a question. If I rearrange the terms, must it converge? What do you think? Give me any series and I rearrange the terms. Suppose a series converges, I rearrange the terms. Do you think the rearranged series has to converge? How many people say yes? How many people say no? Okay, yeah, you probably guessed that because I said something bad was happening, right? So here, so first the answer is no. May not necessarily converge. Do you think if it converges, it has to converge to A? How many people say yes? How many people say no? To A? Turns out the answer is, so if it does converge, does it converge to A? The answer to this is a big resounding no as well. So what I want to show you as a final example is, in fact, an example of why things can go bad. So here's an example. Look at this example. This thing converges, right? Anybody know what it converges to? Oh, come on, some of you must know. Converges to? Log of 2, excellent. But guess what? It not only would a rearrangement not necessarily converge to log 2, but I can get it to converge to any number you like. Really? You give me a number. Give me a number. Steve. Pi. Get it converged to pi. So this is a result due to Riemann. Not the pi result, but if the sum of the ANs converge, but not absolutely, then a rearrangement can have any limit you like. Actually, you know what? It's even worse than that. You can have any lim sup and lim imp you like. So it may not even converge, but you can get it to, you can get it to do basically whatever you want. If it does converge absolutely, guess what? It has to converge to the same value. Okay, so this is what's amazing. So alternately, if it converges absolutely, all rearrangements have the same limit. Amazing fact. And this is one of the main reasons for caring about absolute convergence. Let me show you how to get this series to converge to pi with a suitable rearrangement. Take a look at the odd terms. Would you agree they're all positive? 1, a third, a fifth, a seventh. Yes? What can you say about that series? It diverges, doesn't it? Some of the odd reciprocals, yeah? The other ones are even reciprocals. What can you say about those? That series diverges, right? So those get as large as you like. So the positive terms get as large as you like, yes? So I'm just going to add a bunch of positive terms. And would you agree, Steve, that eventually the sum of these reciprocals will eventually be bigger than pi, just barely? There will be a first time when it's bigger than pi, yes? Okay, now I've overshot. So I'm going to go back. Let's now start subtracting off the odd terms, the even terms. And I'll go far enough back so that I just overshoot pi again. So make sure, so do it so that this is now less than pi, less than pi. And then I'll start where I left off with the positive terms, make it bigger than pi, less than pi, bigger than pi, less than pi, et cetera, et cetera, et cetera. Yep. And you'll get a series that converges to pi. Pretty nifty. Amazing fact about rearrangements. If it's not absolutely convergent, you can get it to do whatever you want. Lim soups, lim imps, whatever. Okay, great. Have fun. We will see you on Wednesday. And on Wednesday, we'll begin start talking about continuity of functions. Okay.